this was a project that Andrew came upon at an internship this summer at Alliance Coal. So to tell you more about it is Andrew Horn.
Thank you all for being here this afternoon. I'm Andrew Horn. That's Dr. Ronald Deersing, my faculty advisor. And this project that I got here was the electrical distribution for the dry storage building / workshop for Gibson County Coal's new Gibson South mine. I'd like to extend my thanks to my family and friends for their continued love and support, the engineering faculty here at USI for all their help, Aaron Brown, Chris Hopple, Marco Hoffman, and all the folks with Alliance who assisted with and approved this project. My faculty advisor, Dr. Deersing, for all his guidance and patience, Dr. Schultz for sparking my interest in electric power and motors, Mrs. Donna Moore for the constant reminders and endless candy dish, my wife Sarah for her love and support and helping me find my way, and last but not least, my daughters, Brianna and Elena, for their love and patience waiting for me to get done this week. Alliance Resource Partners is the parent company of Gibson County Coal. Alliance is one of the top coal producers in the eastern United States. They currently have 11 mining operations across 5 states, including Indiana, Kentucky, and Illinois. They are a large employer of interns from several universities in the area, including here at USI. My internship experience began in May of 2011. Gibson County Coal North, located west of Princeton, Indiana. They began production in November of 2000. Last year, they produced 3.4 million tons of coal, and they have estimated reserves of 18.5 million tons. That was at the end of last year. They employ hundreds of local workers, and I have interned here at Gibson County since May of last year, up to the present day. They're building a new mine, Gibson South. This mine is located near Owensville, Indiana. It's south of the current Gibson operation. Construction began here in 2011. They have nearly 70 million tons of reserves that are currently owned by Alliance Coal. And they're estimating annual production of 3 to 3.5 million tons per year, hopefully starting production by the fourth quarter of next year. Here's some aerial pictures of the construction of Gibson South. As you can see here, this large building, that's the prep plant. That's where the coal is washed and sent on its way to the customers. Here's kind of another look at it. And then there's an even farther away look. That's the whole slope side right there. And then this picture here, I've drawn a circle around the dry storage building on the shaft side. This is the building I am designing the electric for. The dry storage building workshop is used to house large supplies and keep them out of the weather. The workshop for fabrication and repair on a smaller scale for the shaft side is also here. The building also includes a 20,000 gallon water tank for the underground water supply. One of the major functions of the fabrication workshop is to repair and rebuild supply trailers. These trailers are used underground to haul supplies like timber, block, roof bolts to production units and other areas of the mine. Supply trailers are loaded with gear and sit down the shaft elevator and hauled throughout the mine. Here is a photograph of the supply trailer, one of our supply trailers, and if you can tell by the picture, they take quite a beating, so it's very necessary to have the shop there to help repair it. The objectives of this project, to design the electrical distribution, I need to estimate the total building loads, electrical loads, use the dry storage building workshop at Gibson North to estimate what type of equipment will be housed in the new workshop. Find the total apparent power for all the equipment and other building loads using the nameplate ratings. Using single-phase building loads, apparent power, size a single-phase transformer to provide power for all the 120, 240 volt loads. And select the proper square D transformer based on the load estimate calculations. And then also using CED, one of our trusted vendors, research and select equipment such as lighting and heaters. Then put together a construction layout for the contractors that will build the electric in the building. And of course, note the location and size of all the components to be installed. And then get the price quotes from CED for all this equipment. And using another trusted vendor, Valley Electric Supply, research and select the proper equipment for transmission, including load centers, transformers, and circuit breakers. And then I add this equipment to the layout for the contractors and clearly mark the location and size of all this equipment. And finally get price quotes from Valley Electric for that equipment. And then I'll use the layout to get bids from the contractors for the construction of the project. And use the layouts, get the layout and price quotes approved for construction. Place the orders, select the contractor, and move forward with construction. The dry storage building at Gibson North was inspected, and all the nameplate data for all the equipment inside was recorded. The equipment nameplate ratings are given in RMS, voltages and currents. RMS values are equivalent to the effective voltages and currents. Apparent power is given by the effective voltage multiplied by the effective current in units of voltamps. Transformers are rated in how much apparent power they can supply on their secondary sides in kilovolt kVA. Here's an example of one of the apparent power calculations I did, single phase. The magnitude of S, the apparent power is voltage RMS times current RMS divided by 1,000. And here I've used an example from one of the pieces of equipment from the dry storage workshop. It was a bench grinder at 120 volts, 10 amps. Divided by 1,000, you got 1.2 kVA. And here is a list I made of all the equipment I anticipated would be in the workshop. You can see over here is all the items, their quantity, how many there will be, the phase, the voltages, the currents, and the volt amp apparent power. And here is the worksheet I used to calculate the size of the transformer with all the same values except the load I put in kVA, which is how the transformer is rated. The total kVA calculated for the transformer was 44.78 kVA. So the size of the transformer that would supply this apparent power rating was 50 kVA. We use Square D components with Valley Electric, and in the catalog under 600 volt or less nominal drive general purpose transformers. With these ratings, I've selected this transformer here. For the lighting, there are several different types of fixtures that were suggested by the sales rep at CED. There was some T5 fluorescent fixtures for the shop area, some T8 fluorescent fixtures for the dry storage area. LED wall packs were looked at to be installed for the outdoor lights, and LED wall packs were also examined for use in the water distribution building. The Illuminating Engineering Society of North America requires light manufacturers to provide photometric data for their fixtures. One of the most useful types of photometric data is the spacing criteria, or SC rating. SC rating is used to determine the proper spacing for different types of fixtures, so appropriate lighting can be designed for various work environments. The SC ratings were used to determine if the suggested fixtures would provide good lighting for different areas of the building using this equation. The mounting height of the fixture minus the working height times the SC rating equals maximum fixture spacing. The spacing for the lights were concurrently being laid out as these calculations were being done. The SC rating, here's an example, the SC rating for the T5 fixtures was 0.96, and using that equation with the mounting height of about 20 feet above ground, working height about 3 feet above ground, times the SC rating at 16.32 feet, maximum spacing. So I thought they'd be well utilized, spaced 16 feet apart. For the LED wall packs used outdoors and in the water distribution area, those are rated by the mounting height as far as the wattage and as far as the spacing. The spacing for these is listed can be as much as 3 to 4 times the mounting height at the max. The mounting height for the outside wall packs were 18 feet above ground, and the mounting for the water distribution area wall packs were about 10 feet above ground. So for the outdoor wall packs, I chose spacing of about 24 feet. And the LED wall packs for the water distribution lights, I put in all 4 corners of the building to light the areas of the water tank, surrounding the water tank. For heaters, chose the Chromalox HVH model heater. The proper size of this heater was calculated using a worksheet provided by Chromalox. And in that worksheet, you take into account the square footage of the room you're trying to heat, as well as things like the R factors of the building materials that you're using. Using that worksheet, the heater that I calculated the size for was 15 kilowatt HVH unit. Here's a photo of a Chromalox HVH style heater. For the load centers, the incoming power feed had already been determined by project engineers as being a 3-phase 480 volt, 400 amp service. There would need to be a main service panel rated to handle the 3-phase service for all the 3-phase loads, as well as feed the single-phase transformer. There would also need to be a single-phase service to be fed from the transformer and rated to serve the single-phase loads. The load center for the 480 volt 3-phase main was a square D I-line panel with a mains rating up to 600 volts and 1200 amps of current. The load center for the 120 240 volt single-phase service was a square D NQ panel with a mains rating up to 240 volts and 600 amps of current there. The load centers were then selected. They were further broken down by how much space they would allow for the planned circuit breakers, as well as spares. Here's an image of the square D I-line panel, which was used for the 3-phase service, the main service entrance. And there's an image of the square D NQ panel, which was used for the single-phase service. A redesign was required after figuring up the total cost of the project. It was near $35,000, and the project engineers approached us and said that that was way too much. They were looking to be more like $15,000, and that was for the construction of the electrical equipment as well as the parts themselves. So I had to redesign the layout, and doing this, I removed all the fluorescent fixtures, which was suggested to me, because with the fluorescent fixtures mounted at 20 feet above the ground, it can be a pain to have to change the bulbs out, so I can certainly understand that. And then also, a lot of the receptacles, probably about 25% of those were removed. And so not only was there a reduction in the parts, which reduced the price of the parts, but also there was a reduction in the amount of equipment, which would reduce the amount of wiring and in turn reduce the amount of money needed for the construction. Once this was done, the total cost of the redesign layout, parts, construction, everything, was about $23,500 there. And the lead project engineer approved the layout because he's agreed that the building was near bare minimum of what it would need to get going. So went ahead and approved that. Here's a section. This is the workshop section layout for the shop area. This is the final approved layout. Right here, we switched those fluorescent lights to these 400 watt metal halide utility high bay fixtures. Here we have a heater here in this corner, 15 kilowatt heater that gives you guys here receptacles. There's a 68 watt LED wall pack shining toward the back of the building. Here's the communication box, the 480 volt panel, transformer, single phase panel, and then you can see everything else is pretty much self-explanatory except for the 60 amp disconnects for the welders. This is the section for the water tank, for the water distribution area room. And like I said, I put the LED wall packs, the 19 watt LED wall packs in 3 corners here. Reduced the amount of receptacles. We had a 10 kilowatt heater in here. And there's another communication box for the flow meters for the water. And here's the dry storage area, just to garage bay, and we ended up taking all the fluorescent fixtures out of the main area here. We took these 3 wall packs that were supposed to go outside, shine the back of the building, and we just put them inside to shine outward there. And then we still have our 3 shining out from the building. As far as the progress of the project thus far, the parts have been ordered and received from Valley and CED. We selected our contractor, Allied Electric. They actually had the best price, and they were who we all collectively hoped would get the project because we had them on site already and we were very satisfied with their work. Construction began November 1st of this year, and then it was halted days later because they had a building with much more pressing priority that needed to be wired up. So we're currently awaiting completion on the building. I have a few pictures of it. This is the building right after it was built. This right here is the workshop area, and you're looking in the garage bay. And then right there is the water distribution area. Here's the large open bay, and you can see they started storing stuff in there as soon as the concrete was dry. Picture doesn't look great. It's the panels installed without any of the interiors or circuit breakers. This is the large I-line 480 volt 3-phase panel. This is the transformer, 50 kV transformer here, and that's your single phase load center there. And that is the interior of the transformer, which is also dark. And that is one of the 68 watt LED outdoor wall packs wired up. That's what it looks like. And again, I want to thank everyone for coming today.
All right, we're ready for some questions.
Andrew, I have 2 kind of competing questions. When you're sizing your transformer, on the one hand, you got 44 kVA of load that was going to be required, and you picked a 50 kVA transformer. That doesn't leave you a lot of room to grow if they want to put something else into the building.
Right.
And then the competing question on that is, did you consider load diversity? Because you're not going to be using every single thing all on at the same time. And how do you, maybe the 2 questions answer themselves, but could you speak to both of those?
I believe that, yeah, they do kind of answer themselves. The load diversity it will tell you that not all that equipment will be running at the same time. The 50 kVA rating is rated for all the equipment running at full load current all at once. So it does actually leave you quite a bit of room to grow.
But did you consider either of those?
Well,
I mean, it doesn't necessarily balance itself out easily, right? Because you could have maybe a 43 kVA transformer. I don't know, you can buy them in that size, but whatever. That would still leave you maybe 50% room to grow if you had a 50% diversity, right?
yeah, potentially. I just sized it according to the way, the proper way to spec it, by taking the total apparent power of your load that it's going to serve. And it did have a little room in the kVA, and like I said, it's only going to need that much power if it's running everything at once, so it should have plenty there.
Okay.
Nice job, Andrew. Neat project, really neat project. Why didn't they heat the water area? Looks like there was no heater.
There was a heater in there.
Was there?
Yeah,
Okay.
I didn't pick that myself. They said just throw a 10 kilowatt heater in there.
Okay, so you had one included?
Yeah.
Okay, good.
Yes, sir.
Any other questions? No? Okay, let's give.
Andrew, I just had a question. You mentioned that you used the Gibson North plant as kind of figure out what equipment was going to be in there. Do they have the exact same facility? I mean, or a similar facility, and did you kind of compare your design with what the existing ones are?
Yeah, absolutely, I did. But the main thing that was a template for me to see what kind of equipment I could expect, you know, the size of transformer in the total building, power facilities. And I talked to the gentleman that worked in that building as well as the guy that's gonna be working in the new one to make sure there weren't gonna be any curveballs in there, you know. And so, yeah, I used that in the template.
So was the size the same and?
It was a little smaller, but it's pretty well. Yeah, they're gonna, I think, try to lay it out pretty similarly.
All right, let's give him a hand.